All right, welcome back as we go through migration mass transfer for electrochemistry. So first off, let's just consider the current that came from migration. We're not going to worry about convection or diffusion. And we can define this with the charge number of our species. We have Faraday's constant, the area, diffusivity, concentration, universal gas constant, temperature, and then this is the gradient of the electric potential. Now, that is different from the electrochemical potential, and if you need a refresher, I'd encourage you to go and look at the last video for the thermodynamics lesson, and that will give you a little bit more information on the difference between electric potential and electrochemical potential. Now, we define ionic mobilities and equivalent ionic conductivities to talk about, how these things are moving. And then we use these to calculate transference numbers, where the transference for a species is the current that we would just get from that species divided by the total current from migration. And you can see here some things are going to cancel out, and what we're left with is this ratio with either ionic mobility or equivalent ionic conductivity inside. And so transference, it's both a measure of how easily things are moving because of their charge in the electric field, and it also includes some concentration information as well. So we can use these transference numbers to do a really common exercise called a balance sheet. And so what we do is we define our reactions that are going to happen, and you have to include what your solution is made out of. So in this case, it's just HCl. And we're going to say there's 10 electrons flowing every second. We calculate out the ionic conductivities. In this case, these are just tabulated values that we're using. And then we look down here and we can see, oh, hey, look, the concentrations are the same because HCl is dissociating, and their absolute charges are equal to each other as well. So we calculate out the transferences for protons and chloride ions. And then we plug these in here to get out the how many of these protons are moving because of migration. This is the migration section, and how many from diffusion. So you can see here this 0.8, this 0.2, they come up here, they become 8 and 2 respectively. So as these 8 protons, they're positively charged, so they're attracted to the cathode, which is negatively charged. And in their reaction, they'll make 4 hydrogen molecules, and they'll use up 8 electrons. But remember, we have 10 electrons. And so that means that 2 more electrons are going to have to come from the diffusion mass transport. So here we have just what I explained. So we're bringing these numbers up into the migration area of our balance sheet. We remember we have 10 electrons, and then we need to make up, since we used 8 electrons here in migration, we need to make it up with 2 more electrons. Now, the same thing is going to happen over on this end, where only 2 electrons have come from the chloride ion migrating, and so we're going to have to make up 8 more electrons through diffusion. So the important thing that I want you to notice is that even though we have a high transference here of 0.8 for the protons, you'll notice that only 20% of the total current is coming from diffusion. 80% is coming from migration for protons. So I'll remind you of that again in a few slides as we go over another one. So let's talk about the effects of migration on our measurements. So this was a little study done by Michael Stoddart. he was doing some simulations, including migration. These are cyclic voltammograms, and this is the dimensionless current. So you'll notice here that the gray value, that's the Berzins-de equation. That's if we're not considering migration, that's what we would see. And you'll notice that the green and the red signals are very close to that. So at low concentrations of uranium chloride, the currents that you measure are about equivalent to if you didn't consider migration at all. But once you get to higher currents, then higher concentrations, then your currents begin to differ quite a bit. So these blue and this orange, you can see they're quite a bit different than if we neglect migration. So migration plays the biggest role when our analyte is highly concentrated relative to the electrolyte. Now, you'll notice here that in this case, he was assuming that the uranium was, it's in a 3+ state, and he's assuming there's no complexation with the chloride ions. And so uranium in this case is a positive species. And so he's doing a reduction. And so when he considers migration, he actually has an increase in current because he's considering migration. So that's what you would expect if you had a positively charged ion moving or being pulled by migration to a negatively charged cathode. But the opposite is true if you take your uranium chloride. This again the uranium is in a 3+ oxidation state. This time it's just complexed with chloride ions. And in this case, you'll notice that the currents, when you consider migration, are actually depressed. And once again, this occurs when you have a concentrated species. When it's dilute, it doesn't make much of a difference at all. So supporting electrolyte, we kind of just saw the importance of that. What we're looking for in a supporting electrolyte is we want it to be highly soluble. And the reason why is because if we can get a lot of it in there, then the supporting electrolyte will carry almost all of the migration current, and that makes it so that our analyte just has to move by convection. We can predict that, and with that prediction in using differential equations that we've talked about in previous lessons, we can predict the currents that we get. So some other things that we want out of our supporting electrolyte, we want our supporting electrolyte to be electrochemically inactive at the electrode surface. So we don't want there to be any reductions or oxidations near potentials where our analyte is going to be reducing or oxidizing. So we want a wide electrochemical window. The electrochemical window is defined by where either our electrolyte or our, base solution begins to break down electrochemically. And the region where, no reactions are happening in our supporting electrolyte or our solution, that's the electrochemical window. So some examples of supporting electrolyte may be, salts are often used. And in molten salt cases, like lithium chloride, sodium chloride, calcium chloride, the really nice thing is that your solution is actually the same as your electrolyte. So that makes it really easy to have high concentrations of your supporting electrolyte in molten salt situations. So some advantages versus disadvantages of having a supporting electrolyte. The first is that for advantages, you decrease your ohmic resistance, so you're not wasting as much energy. Your cell analysis is simplified because you only have to consider diffusion. And the double layer thickness is reduced. Some disadvantages is impurities in your supporting electrolyte can interfere, or even your electrolyte itself can interfere with reactions that are going on. And they can just change the properties of your solution from its pure state. So those are some of the things that can mess you up. So here's two questions that I want you to go ahead and do your best at. The first is, when do you need to consider migration? And the second is, if your analyte is positively charged and you're reducing it, would you expect enhanced or diminished currents? So go ahead and pause the video, and I'll give my answers in a few seconds. All right, so you need to consider migration when your analyte is concentrated with respect to your analyte. And a figure that we've seen tossed around in literature is if there's more than a 1:30 ratio between your analyte and your supporting electrolyte, then you need to start considering migration. So if you have a positively charged analyte and you're reducing it, we would expect there to be enhanced currents, because your positive analyte will be attracted to the negatively charged electron. So this video, I have another question. I have a fill-in-the-blank balance sheet for you to go through too. Just to orient you, and then I'll let you loose. This is 1 molar sodium chloride and 0.015 molar HCl. We're going to talk about 100 electrons being exchanged per unit time. And you'll note that the reactions are hydrogen evolution and chlorine evolution. So the sodium chloride isn't participating. This is just the supporting electrolyte, and their analyte would be the HCl. Here you have your ionic conductivities, and so I'll pause for a little bit and let you work through what you can, and then once you feel like you're stuck, hop back in, and I'll give you the next steps. Okay, so first, I hope you did your transference number calculations. You should have ended up with numbers like these. So your protons 0.04, your chloride ions 0.58, and your sodium ions 0.38. Okay, so if you were only able to get to there, go ahead and pause it again and try to work through a little bit more, and then I'll continue on in a few seconds. Okay, let's continue on. So we're going to take our transference numbers, and we're going to remember that we're looking for 100 electrons, and we're going to put them up into our balance sheet. So here we have 4, 38, and 58. It's coming just straight from these transference numbers. Okay, so this is the next step. Once again, go ahead and pause it if you were just stuck going there, and see how far you can get. Okay, so let's start counting up electrons that are being transferred. So if 4 electrons or 4 protons are being moved across to the cathode by our protons, and there's going to be 4 electrons used up, we're going to make 2 molecules of hydrogen. So the question is, what do we do with the other electrons? Go ahead and pause it and try your best, and then you'll see what we can get. Okay, so the rest of the electrons are going to come from diffusion down here, and we'll have 96 protons moving through diffusion, 96 electrons here, and we're creating 48 hydrogen molecules. Okay, so now go ahead and try to do the anode side on your own, and then I'll talk through that. Okay, so on the anode side, here we have 58 chloride ions. That means 58 electrons as it's being oxidized, making 29 chloride molecules. And then we need to make up the rest of the 100 electrons. And so we're going to have, 42 protons, 42 chloride ions, 42 electrons, and 21 more chloride molecules. Okay. So that concludes the video on migration and the lesson on mass transfer. Hope you enjoyed it, and we hope that you'll tune in on some of our other videos.